Good morning, everyone. I request Himanshu sir to conduct the session.
Good morning, sir, and good morning, students.
Good morning, sir.
Okay, I'm sharing my screen. Do let me know whether it is visible or not.
It's visible, sir.
Okay, done. Thank you. So in the last class, we have discussed about the sigma and pi bond. So let's start with the discussion of sigma and pi bond. But I want you to tell me the difference between the sigma and pi bond first. Okay, I'm writing sigma over here, sigma bond, one side pi bond. Okay, first difference between sigma and pi bond. First, anyone? One difference, just one difference. See, in sigma, it was side by side or head on head.
Head on head.
Head on it.
Head on head overlapping. And pi,
Side by side.
side by side. So, basic differences. See, mute from yourself. Sigma is head on head and pi is side by side. I'm getting my voice back, please. Okay. Second thing, in sigma and pi bond, in case of sigma, more extent of overlapping. More extent of overlapping. While in case of pi, there is a lesser extent of overlapping. Okay, what happens when the overlapping is more and overlapping is less? Bond is strong. If overlapping is more, then it means the more attraction force is there, more strong the bond is. And here bond is weak. Fourth difference between sigma and pi. There is a free rotation around sigma bond. While in case of pi bond, there is a restricted rotation around the sigma bond. Okay, one more difference, last difference I'm taking, 5 difference is enough. In case of sigma bond, s orbital can participate. This is a very easy difference. You can say s orbital can participate in the sigma bond, while in the case of pi bond, s orbital cannot participate. This much is enough for the difference. If any point you want to ask, just ask me fast. Nothing? Okay. Then let's start with the new topic that is known as hybridization. Okay. First of all, what hybridization is. So we'll go for the definition. The basic definition is the process of intermixing. The process of intermixing of what? Intermixing of the orbitals. Intermixing of the orbitals. Which type of orbitals? Orbitals of slightly different energies. It means those orbitals which are having a slight difference between their energies that undergo the intermixing. And what they exactly do, they used to redistribute the energy. So the process of intermixing of orbital of slightly different energies, for which, so as to redistribute their energies and set new orbitals of equivalent energy. See, definition is into parts. Okay, the first part it will go, that is the process of intermixing of the orbital of slightly different energy. First point you have to remember that under the hybridization category, what I'll study, that there is an intermixing of orbital, only those orbital which have only a small difference between their energies. Second thing, when they are intermixing, second thing you have to remember, that is redistribution of their energies. So as to redistribute the energies, they are intermixing. And when there is a redistribution, what will happen? There is a third thing, set of new orbital of equivalent energy and shape are formed. Definition, any problem? Three things: process of intermixing, second, redistribution of energies, third, new orbitals will form and with with equivalent energies and shape. One more thing. See, I told you three things here in the definition. One more thing you have to remember, the orbitals. The orbitals formed as a result of what? As a result of hybridization. As a result of hybridization is known as what? Hybrid orbital. Hybrid orbital. Or you can say hybridized orbital. Okay. So the orbitals which are formed as a result of this particular hybridization is known as what? Hybrid orbital. Clear the definition?
Yes, sir.
Okay. Let's go for the characteristics of the hybridization. So the first characteristics, if I talk about the first point, you can say the number of hybrid orbital. Number of hybrid orbital which are formed must be equal to the number of orbitals that get hybridized. See, if number of the orbital which are undergoing hybridization is 2, then the number of hybrid orbital which are formed after hybridization must be 2. It means the number of hybrid orbital which are formed as a result of hybridization must be equal to the number of orbital which were taking participate in the hybridization process. So the number of orbital must be same. This was the first point. If I talk about the second point, the hybrid orbital. See, I told you in the definition. What was the definition? A new set of orbital of equivalent energy and shape. So this is the second point. Second characteristic, you can say that the hybrid orbital always have equivalent energy and shape. Equivalent energy and shape. Okay. If I talk about the third point, which is important also, that hybrid orbitals are more effective in forming stable bond. See, if I talk about the stability, in case of atomic orbital which were pure and hybrid orbital. Hybrid orbital. Hybrid orbital are always having the more stable bonds. Okay, just because there's a mixing of the energies and they are forming quite a stable bond. Fourth one and the last one, the hybrid orbitals are generally directed in space, or you can say this the hybrid orbital shows a geometry of the molecule. So it means you can say it indicates the geometry of molecule. Geometry of molecule. And these were the four characters that a number of hybrid orbital must be equal to number of that orbital which were taking participate in the hybridization. Second thing, equivalent energy and shape must be there. Third thing, hybrid orbital will always form the stable bond as compared to the pure atomic orbital. See, when the pure atomic orbital undergo hybridization, they will form the hybrid orbital. But before that, the pure atomic orbital were not forming that much stable bond. So the hybrid orbitals are forming stable bonds. Next, fourth point is that it indicates the geometry of molecule. See, as I will start this particular hybridization topic, so you will see the structures and the geometry of the molecules according to the VBT and the VSEPR theory. Okay, so what are the conditions? What are the conditions which are necessary for hybridization? First condition is only that orbital present in the valence shell, only the orbital which are present in the valence shell. But which one is the valence shell? Which shell is known as valence shell?
Outermost cell.
Outermost shell. Okay, so I said only which orbital? Only those orbitals which are present in valence shell. Those who are present in the valence shell undergo hybridization. See, points you have to remember. Sometime when you forget the point, you cannot calculate the answer, you cannot tell the answer easily. I said only those orbitals which are present in valence shell. Okay. Second condition is those orbitals which are undergoing hybridization should have almost equal. So I told you in the starting that is slight difference. So you can slight different and almost equal is approximately the same thing. I'm not talking about a large gap between the energy. So the orbital having the large gap cannot participate in the reaction. Okay. So hybridization. So I'm talking about the large difference in energy and the small or negligible difference in energy. Which one undergo hybridization? Only the small one. Hybridization takes place, while in case of large difference, there is no hybridization. So in case of large difference in energy between the atomic orbitals, there is no hybridization. While in the case of small or the negligible amount of energy, then it is known as what? They undergo hybridization. Third point, if I say there is no essential condition for what? For promotion of electron. Promotion of electron prior to hybridization. It means before hybridization, there is no promotion of electron. What is promotion of electron? It means from the low energy level to the higher energy level. You can say the orbitals which are empty, the electron used to jump in that. So this is not essential. Okay. And the last point is, fourth point, in the condition that only Fourth point is only those orbital will take participate in the bonding which are half filled. Wait, this condition is only those orbital. No, it is not necessary. In case of VBT, it is not necessary. It is not necessary that only half filled will undergo. Half filled orbital participate. What in certain cases, even the orbital of valence electron undergo hybridization. See, generally, half-filled orbital were taking participate in the hybridization, but what exactly happened? Sometimes the electrons which are present in the valence shell orbitals, they can easily undergo hybridization. So you'll see when this chart is going for the examples, you'll see there is a possibility of orbitals which are not half-filled. They are more than half-filled. They are also undergone hybridization. Okay, so you'll see condition. I'll tell you the condition while I'll go for the example. So first type of hybridization. First type of hybridization is sp hybridization. See, if I talk about sp hybridization, what is sp hybridization? When 1s and 1p, when 1s and 1p orbital and are hybridized, when 1s and 1p orbital hybridize and form equivalent orbital, and the equivalent orbital formed, they both get hybridized and equivalent orbital, that is hybrid orbital, is formed. Hybrid orbital will form, and which hybrid? The hybridal is known as sp hybridized. Okay, so for calculating the s character and p character, just because we'll determine the properties later about the s character and the p character, but right now S character is 50% and P character is 50%. It's quite easy. See, 1 and 2. This 2, the 100 divided by 2, that is equals to 50%. It means 50% is S and 50% is P. It's a basic thing. Total character must be 100. Okay, so if 2 orbitals are there, just divided by 2. So that is 50% S and 50% P orbital. So let's start with the example. The example I'm taking is of BEF2. Okay. Anyone just tell me the configuration of BE?
1s2.
1s2 and
2s2.
2s. Atomic number is
4.
4. Okay. So in the ground state, first I'll make ground state means when the electrons are not excited. I'm making this is, see, BE is the central atom. So I'll make this ground state of central matter, central atom. So in B, this is 1s, this is 2s. I'm taking 1, that is 2p, but we don't have electron in the 2p, so I'll show it as 0. Okay, so in the p orbital, we know that it's of 3, that is px, py, and pz. So in 1s of B, we have 2 electrons. In 2s of P, 2s of B, we have 2 electrons. Okay, so if I'll make the excited state, what will happen? 1s will be remain as it is, but in case of 2s, one of the electron will jump from here to here. This is called promotion of electron. As the fluorine atom approaches the beryllium, what will happen? One of the electron from the 2s orbital will jump from 2s to the 2p. So now we have one electron available in 2s and one electron available in 2p. Now how many fluorine? Now I'm making BeF2. So you have to make it again. This is 1s, this is 2s, and this is 2p. We have one electron. So how many fluorine is there?
Two.
2. So this is one fluorine and this one is another fluorine electron. One electron. See, we know that if the electrons are present, see, in the case of 2p, just in the case of 2p, is 2p is half filled? Is 2p is half filled? Only one electron is present. Half filled means in the p orbital, you know that maximum 6 electron take part. But right now we only have one electron, so it is not fully filled, it's not half filled, it's only one electron present in the first orbital. So one electron of fluorine I'm putting in here, another will be here. This is fluorine, this is fluorine. Now just tell me which orbital is participating in the hybridization. One orbital of s and one orbital of p. So one s and one p. The hybrid orbital formed is known as what? sp hybridization. Understanding?
Yes, sir.
So when
Yes, sir.
one s and one p was hybridizing is known as sp hybridization. So if I'll talk about the shape of sp hybridization, B is the central atom, then one fluorine, then one fluorine. This is a linear sort of structure, and the bond angle between this is 1/2 degree. Okay, the name of this shape is linear. Clear?
Yes, sir. Yes, sir.
Okay, let's go for the another example, and I'll second type of hybridization. Okay, I'll go for one example. You can revise it. If you have any doubt, you can ask me in the next class. Okay, second type of hybridization is sp2 hybridization. Okay, what is sp2 hybridization? 1s and
2p orbitals.
2p orbital will undergo hybridization, and the hybrid orbital formed is known as sp2 hybridized. Okay, s character and p character. How much?
33.3.
33.33 S character and 66.66% P character. Do you, everyone know how we have to calculate this S and P character?
No, sir.
See, in sp2, how many orbitals are present? 1s and 2p. The total number of orbital is 3.
3. Yes,
Total
sir.
number. Okay, so just divide 100 by 3. So if you divide it, it will be 33.33. So one S is there. So we gave S as 33.33. The rest, if you minus it from 100, it remains as 66.66. So this will be around 66.66. So this is a simple criteria. Number of orbitals, just count the number of orbitals in the hybrid orbital and divide it by the number. Okay. So let's go for the example. Yeah. Speak. Hello. You want to ask something?
No, sir.
Okay. Example is BCl3. Okay. What is the central atom? Boron. Atomic number?
5.
5. Configuration? 1s2,
1s2 2p3.
huh?
1s2 2s2
2p1. Very good. Okay. So ground state 1s 2 electron, 2s 2 electron, 2p only 1 electron is present. What will happen in the excited state? 1 electron from the 2s will jump in the 2p. So one of the electron will jump in the 2p. This is 1s. 2s have 1 electron now. 2p have 1 electron. And 1 electron which was jumped. So if I make the structure of BCl3, 1s remain as it is. 2s with 1 electron. 2p with 1 electron. Now if I'll go for the filling of Cl, so this is 1 Cl, this one is another Cl, this one is another Cl. So 1s and 2p orbitals are formed. 1s and 2p orbital undergo hybridization to form this sp2 hybridized. So the hybridization here is known as what? sp2 hybridization. If I talk about the shape, boron, chlorine, chlorine, chlorine. Just join this.
Trigonal planar.
That is very good. Trigonal planar. And the bond angle is 120 degrees. Okay. Any doubt?
No, sir.
No, sir.
So just do one thing. Yes? See, either I am hearing my voice again or someone is saying something and is not repeating. So
No, sir. Your voice is
Your voice,
resounding.
sir.
my voice is clear, na?
I
Yeah,
mean,
sir,
your
it's clear
voice
now.
is resounding, sir.
Okay. I'm taking the example of now CH4. Now, I'll not write the type of hybridization. I'm directly doing the hybridization. Just tell me atomic number of carbon.
6, sir.
6.
Configuration
1s2 2s2
yes, 1s to 2s and 2p 2. So ground state 1s, then 2s, then 2p. In excited state, one of the electron will jump from 2s to the 2p. So this is 1s, this is 2s, this is 2p. See, we can go for the shortcut, but first we need to learn this thing. I'll tell you the shortcut also, but not right now. First, I need to tell you the concept. So, one hydrogen, another hydrogen, another hydrogen, another hydrogen. Now, which type of hybridization? 1s and 3p.
P.
So, hybridization is
sp3 hybridization.
sp3. So, this is the example of third type, that is sp3 hybridization. Okay. So, if I talk about the shape of this sp3, this CH4 molecule, carbon will be present in the mid, hydrogen, 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 and here again, hydrogen. Just join all these. Okay, the bond angle between this is 109.5
28 minutes.
degree, or you can say 28 minutes or 5 degree. Okay, the shape is
Tetrahedron.
tetrahedral. Okay, then any other example of tetrahedral shape with the same hybridization? or pyramidal shape, you can say in that case. Okay, just I'm giving you one example. Just tell me the hybridization. Okay, NH3.
sp3, sir.
It's sp3. Yeah, very good. And the shape is, see, the shape of sp3 here in this particular case is pyramidal. Later on, I'll explain why. Okay. Next, go for the fourth type. That is fourth type, sp3d. sp3d. Okay. So let me give you one example. Okay. You have to do PCl5. Okay, configuration. See, I'm writing the last configuration of directly phosphorus. Phosphorus last configuration is 3s2 3p3. You can calculate 1s2 2s2 2p3s, something like this. Okay, atomic number is phosphorus of 15. Okay, so if we'll make the ground state, of phosphorus, then it will be 3s 2 electron, 3p3 3 electrons, and I'm taking 3d as 0. How many orbitals are present in the d?
5.
5.
5.
Can anyone name them? Anyone?
X square is y square, z square, x square minus y square, sir.
So this one is 3. No? X square minus y square. See, 5 orbitals are there. D, xy, d, yz, d, zx, d x square, y square, d z square. Okay, just note it down somewhere so that you will remember this. Okay, so now we have 5 orbital in the d. So I'm taking 3d as empty. So we'll go for the excited state. Then this is 3s 3p3. 1 electron from the 3s will jump in the 3d orbital, and we have 1 electron empty. So for the PCl5, now how many unpaired electrons are present?
5.
Wait, 1
4.
2 3 5. 1 in 3s, 3 in 3p3, and 3d have 1 electron. So we have 5 unpaired electrons. So now I'll go for the PCl5. Then 3s is having 1. Then 3p3 is having 3 unpaired. Then 3d having 1 unpaired. So let's go for the hybridization. Cl1, 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 Cl1 here, Cl1 here. So now just count 1 3s orbital, 3 p orbital, 1 d orbital. So the hybridization is sp3d.
Yes.
Can anyone tell me the shape if you have
Sir,
learned earlier?
trigonal bipyramid.
Pyramid also.
Trigonal bipyramidal. See, phosphorus in the mid, Cl, Cl, Cl. Okay, here Cl, here Cl. Okay, just remember the axial bond are quite longer as compared to the equatorial bond. Okay, so this structure is known as trigonal bipyramidal. Trigonal bipyramidal. Okay, next type. One more next type example, that is sp3
D2.
Okay, d2. Yeah, d2 is also d2. What will be the definition when 1s 3p and 2d orbitals hybridized together to form a hybridization to form a new set of orbital known as sp3d2. Okay, so the example we will take as SF6.
SF6.
Basic examples. Okay, see, if you learn one example, then you can go for the multiple examples just because the hybridization type is same. So if I'm taking SF6, you can take another example. Okay, so basically I'm talking about the SF6. So what is the atomic number of sulfur? Atomic number of sulfur.
16.
16, sir.
16, sir.
Okay,
Yes.
ground state. I'm taking the last configuration directly. That is 3s2, 3p4. And I'll take 3d as 0. So ground state of S is 3s, 2 electron, 3p, I have 4 electrons, 3d, I have 0 electron in the ground state. What will happen? Now 1 electron from the 3p and 1 electron from the 3s, they will jump in the 3d orbit. So in the excited state, 3s, 3p and 3d. Now how many unpaired electrons are present?
6 unpaired electrons.
6 unpaired electrons. So we have SF6. So for forming the SF6, I have 6 fluorine atom. So what will happen? They will put the electrons here, 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 and here. So 1s, 3p, and 2d orbital undergo the hybridization. So it is known as what? sp3d2 hybridization. Okay, what is the shape?
Octagonal, sir.
Octahedron.
Octahedral. Yeah. So S will be in the mid, 4 fluorine atom on its side, then 1 fluorine above, 1 fluorine down. This is known as what? Octahedron. Okay. Next type is sp3d3. Okay, I'm taking example of IF7. Configuration of iodine in the last, that is 5s2, 5p6. Okay, you can go for the total configuration according to the atomic number. So ground state S, 2 electron, 5s, 5p, 8, 5p. Okay, this is not 5. This is not 6. This is 5. 5 to 7. Okay, yeah. So 5 unpaired electron, 1, 2, 3, 4, and 5. If I talk about the D, 5D will be taken as 0. It will be taken as 0. Okay. Now 1 electron from S, 2 electron from P. They will undergo promotion of the electron. So for the excited state, we will see that 1 electron will remain in the s orbital, 3 unpaired electron will remain in the p orbital, 2 electron will jump in the 5d orbital from the p and 1 from the s. So it will be how many unpaired electrons? Now 7 unpaired electrons are present. Okay, so like when I make IF7, I'll see 1, 5d, 5p, 5s. Okay, for 1 electron of fluorine, 1 electron of fluorine, 1, 1, 1, 1, 1. Now the 7 orbitals are hybridized. So 1s, 3p, 2D, sp3d2. Shape, a geometry you can say. Geometry,
Sir, SP3 and D3.
D3. Nee, I'm talking about the shape, okay. This is D3. Shape. That is
Pentagonal pyramid also.
pentagonal bipyramidal. Okay. So we have to make a pentagon in the mid and then two pyramids. Why it is known as pyramid? Can you show the, if you see, I'll tell you now. The shape. Iodine. Okay. This one is fluorine, 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 and fluorine. Just join them. So this is pentagon, one fluorine above the plane, one fluorine below the plane. So this is called pentagonal bipyramidal. See, it is like this. Iodine, fluorine, 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 and one more is there. Fluorine. Sort of, if you'll see why I'm saying it's bipyramidal, if you'll join these structure, join this structure, one pyramid like structure is forming above the plane. It will join with this particular fluorine atom. One pyramid will form at this plane. So two pyramidal sort of structure is there. And in the mid, we have five. Five represent the penta structure. So that is penta for the five, pentagonal for the electron, the orbitals which are presenting in the horizontally. While above the plane and below the plane, they are forming a pyramid-like structure. That's why it is known as bipyramidal. Bi represent two, pyramid represent a formation of cone type of structure. Okay. Clear? Clear?
Yes, sir.
Yes, sir.
Okay. So wait. So one more type of bond, I'll tell you, that is DsP2 hybridization. See, in addition to all those type of hybridization, we have one more type that is called DsP2 hybridization. And in this type of hybridization, this is particularly occurring in the transition metal. What are transition metal ion? What are transition metals?
D block
elements.
elements.
P or D?
D.
Sir.
Yeah, D block elements are known as what? Transition element. So in case of the transition element, this type of hybridization takes place, and there is an involvement of the orbital which are involved in this particular hybridization, that is dx square y square s and 2p. The orbitals which are participating in the hybridization here, that is called dx2 y2 of d s and 2p. So just remember this thing. This is quite important. You can remember easily. So the example I'm taking is NiCN 4 2 negative. See here Ni configuration. Can anyone tell? At okay, atomic number. It's 28. Configuration will be AR 3D8 4s2. Okay. So nickel in the ground state. Nickel in the ground state. D orbital. How many electrons? 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and then 8. 4s is taken as 2 electron. And I'm taking one p orbital which is empty. Okay. This is D, this is S, this is P. Okay, if I'll go for the excited state, what will happen? Nickel is present here in two positive form. See, how can you tell whether it is positive or negative? See, take this structure. If I have to calculate the oxidation state of nickel, we have to take it as X plus. Cn is always -1. The charge on Cn will be -1. So 4Cl is there, so -4 is equals to -2. So X minus 4 is equals to -2, X is equals to +2. So now if we can easily see that Ni is in the +2 state. So +2 means just remove the outermost 2 electrons. So these outermost 2 electrons are gone. So we have d orbital in which 1, 2, 3, 4, 5, 6, 7, and 8 electrons are present. Okay. And S is empty now, and P is also empty. Now,
Sir,
if
can
I'll
you
go
explain
for,
once again
yes,
that how X is positive, sir? Can you explain once again?
see, this +2. See, the charge on the Cn is -1. So 4 atoms are present. So -1 into 4 is equals to -4. The element which you have to calculate, you have to always calculate the central metal atom. So central metal atom is nickel. So I'm taking it as X plus. You have to add all the things. Cn is equals to -1 into 4, -4. The total charge on this complex is -2. So I'm putting it as -2 here. If there is no charge, you'll write 0 here in place of -2. So now just calculate the value of X. You know this much calculation now, that how you have to calculate this.
Yes, sir.
Yeah. So just the elements which you have to calculate the oxidation state of that particular metal, you have to take it as X, and rest you have to put the number. See, you will learn this particular thing soon. Don't worry, this is quite new for you. This is the complexes, these are coordination complexes, you can say. So I'm giving you this example just because so that you'll not, if someone will ask you that if DsP2 hybridization occurs or not, then you can give at least one example. Sorry. Okay, what will happen in this particular case? The electrons present in the d orbital shift inward and paired up with its own electron. What will happen? The electron present here in the outermost will paired up with the electron itself. So now we have 1, 2, 3, 4, 5, 6, 7, 8 paired electrons. And you can see 1, 2, 3, 4, 5. 5 places are empty I have. And Cn negative. Now Cn will put its electron here, 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 and here. Because 4 Cn is there. So 1 Cn, 1 Cn, 1 Cn, and 1 Cn. Okay. So 1 orbital of D, 1 orbital of S, and 2 orbital of P are hybridizing together. So they are forming DsP2 hybridization. The shape of this is Ni, Cn, 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 and just join them. And total will have 2 negative charge, and this structure is known as square planar. Clear? Okay. One thing you have to remember. In sp3d, dz square participate. In sp3d, 2 dx square y square and dz square participate. In sp3d3, that is dxy, dyz, and dzx participate. While in case of dsp2, dx square y square. Question can be asked on this also. Okay. So any doubt in hybridization, that how we were calculating the hybridization? Then I'll give you one. If you don't have doubt, I'll give you one table. Okay. You can have more example from that particular table. Any doubt?
No, sir.
So, okay. So should I wind up this class? Today I will share this notes. So this contain all the things, whatever you have. I'll convert into the PDF and I'll send you today. Okay. Just revise this much for your test, that as till the hybridization. The concept you have to remember, that is, first thing is bonding. Second thing is types of bonding. Fourth thing is formal charge. Fourth thing you have to remember, that is VBT, then hybridization, and along with their minor topics also. Just revise it from your book. You'll have your test, and I'll give you some questions. Okay. Okay. Let's wind up the lecture and go. You can join your next class. Thank you so much.
Thank you, sir. Students, join the next session.